Okay, so let's move on. Let's talk about one other idea, and then we're going to look at emerging technologies. This is actually a fun idea. I like talking about it. So if you look at today's memory, how many of you have done things like memset or memcopy? You use that, right? How many of you have done it for large data structures? Have you ever memcopied a huge array? Yes. Is it slow? Okay. So we're going to try to accelerate it. So if you look at today's memory, if you want to copy one page, I'm going to say one page, but you can actually think about other granularities. But let's operate at the level of one page. If you want to copy one page to another page, it's very inefficient today. What you need to do is the processor needs to send loads, and byte by byte, you copy the page all the way to the L1 cache, and byte by byte, you write the data back to memory at some point. Right? Basically, the entire page copy is gets copied byte by byte. Now, there are many downsides to this, right? First of all, this takes high latency. There's a huge round-trip delay. Second, this consumes a lot of bandwidth in the memory, on the off-chip pins. Right? Third, this leads to cache pollution in the cache. And fourth, this has unwanted data movement, a lot of unwanted data movement. Now you can optimize this by doing DMA transfers, right? You can actually set up a DMA and you can copy pages through this loop without going into the caches. That gets rid of the cache pollution, but that doesn't get rid of all of the other problems. So we'd like to do basically this. We'd like to say to the memory controller, copy the source page to the destination page. And that's it. And the memory controller does this. That's the idea, basically. And you already know how to do this, actually, because we've discussed it in the context of tiered latency DRAM. Basically, this leads to low latency because the copying or initialization is done in memory. This leads to low bandwidth utilization because you don't consume any data bus bandwidth because the memory does the copying itself. No cache pollution, and no unwanted data movement. So how do we achieve this? And I already said that you actually know how to do this. Basically, today's DRAM operates at a large granularity, right? A row. It could be 4 kilobits. It could be even larger. Basically, in order to read some number of bytes, you need to activate the row, which places the data into the row buffer. And some number of bits get transferred onto the bus through the data pins. Now, if you like to copy one row to another, it's relatively easy. Right? You just need to activate the source row, row A, which brings the data into the row buffer. And then you need to activate row B. Right? What this does is this basically takes, this way the row buffer actually drives the bit lines and drives the data into the destination row. That way you copied row A into row B. Right? It's simple. So this, of course, works if these rows share bit lines, right? Share the local bit lines that I've shown you earlier, which means that if these rows are within the same subarray. And that's the idea. That's the idea of the row clone. The key idea is DRAM banks contain multiple rows of DRAM cells. A row can be 8 kilobytes if you look at a DIMM, actually. A row is shared by the DRAM rows. And if you want to do a large-scale copy, generalizing, you can copy data from the source row to the row buffer, and you can copy data from the row buffer to the destination row. And this can be accomplished by 2 consecutive activates if source and destination rows are actually in the same subarrays. Now, if you go and do this in today's DRAM chips, it will not allow you to do this because it doesn't accept the second activate. Or actually, I don't know what it does with the second activate. This is something to experiment with. But it won't work. But you need to, basically, the second activate, basically you need to change the DRAM such that the second activate deactivates the first row. Okay, so why does this work? This is the intra-subarray. We've already looked at it. Assume that this is the data you have in the source row. This is the data you have in the destination row. And we would like to copy the source row to the destination row. If you actually activate the source row, this is what we get. Sense amplifiers have the same data as the source row. And later, let's assume that we deactivate the source row. Actually, you don't necessarily need to do this. You can do it implicitly. And we activate the destination row. If you actually activate the destination row, now the sense amplifiers start driving the destination row. because the sense amplifiers are much more powerful than the cells over here. That's the charge sharing principle. And sometime later, the destination row gets the value that is in the sense amplifiers, which was driven by the source row to begin with. That's the idea. So we would like to generalize the idea, of course. We don't want to do the page copy only within the subarray. We'd like to be able to do it across banks and across subarrays as well. So let's take a look at the case where you actually have a source row that's in one bank and a destination row in another bank within the same DRAM chip. If you would like to do this, this is a little bit, it's not as elegant as the previous one because these do not really share a row buffer, right? So what we're going to do is to have a transfer mechanism, a transfer command with which the memory controller basically reads the data at the granularity of the I/O bus within the DRAM chip. This is the I/O bus within the DRAM chip. Brings the data and writes it to the destination row over some number of cycles. So of course this won't be as fast, but you will not consume memory bandwidth this way. If the worst case happens when you actually have two rows that are in the same bank but in different subarrays. In this case, you cannot copy directly through the local bit lines, and you cannot copy directly through the global bit lines because when you're reading a row, you cannot write to another row through the global bit lines. So what we're going to do is to have a temporary row on some other bank allocated. We're going to take the source row, bring it to the temporary row through the transfer command, and then we're going to take the temporary row and move it to the destination row through another transfer command. Now this takes, of course, longer. This happens when the source and destination rows are in different subarrays. Okay? Okay, so you can actually use this mechanism to initialize rows. For example, how many of you have initialized arrays to zeros or some values? Looks like the same people who copied arrays also have done initialization. And that takes some time? Okay. This actually takes some time if you have huge memory machines, database machines, for example. But you can actually fix a row at all zeros. Zero initialization happens a lot in some benchmarks, in some workloads. This gets you a loss in capacity, but you could actually do this in a software-controlled manner also if you add enough exposure to the software. But if you want to initialize a destination row to zeros, what you can do is basically do an activate of this row and an activate of the destination row, then you have the destination row set to zeros. That's the idea. So what's the benefit of all this? This actually leads to significant latency and energy savings because you don't bring all of this data all the way into the memory, all the way into the processor. So I'm showing you latency benefits over here. The baseline, it's normalized to the baseline, and I believe baseline, let me take a look at the baseline here. So in the baseline, it takes 1,046 nanoseconds to do an entire page copy. If you have intra-subarray copy, it takes 90 nanoseconds. So you get actually more than 10x latency reduction. This actually translates to a 74x energy reduction because you're reducing energy even more. You're not utilizing any of these buses. It's all internal. Let me go back. So that's where the energy reduction comes from. If the source and destination are actually in different banks, you still get some latency reduction. And you still get some energy reduction as well. If the source and destination are in different subarrays, you don't get that latency reduction, but you still get some energy reduction because you're not going off chip. Everything is happening internally within the DRAM. And the memory controller is orchestrating that data movement in the DRAM. So obviously you can see that depending on where your source and destination rows are located within DRAM, you get different latency and energy benefits. So data mapping, again, matters here. So it may, if you have this mechanism, it makes sense for the operating system or the system software to allocate the destination page in the same subarray as the source page so that you can do the copy really fast. And this could be done in some cases. If you're doing copy on write, if you're allocating at that point in time, and if you have control over subarrays, you can hopefully do this. And of course, you have to expose the subarray information to the system software to do that. Okay, I'll let you read the technical report if you're interested in this. But going forward, doing such large-scale operations in DRAM, I believe, is a very interesting research direction because there's no reason to move that data all the way to the processor if it just makes sense to do that copy somewhere else where that data already is, right? unless you need that data. So let's take a look at some real application results. Take this with a grain of salt. So this is actually an area where it's difficult to evaluate the benefits because a lot of software tries to avoid these page copies. I know you have programmed these with these large mem sets and mem copies, but a lot of software tries to avoid this, like the plague, if they want to minimize the cost of these. So it's hard to find applications that do these large-scale page copies. But there are some, like database applications, memcached, and some shell applications. Actually, operating systems do this a lot, the initialization. I won't go through this in detail, but if you do this in a not smart way, if you just say all page copies are done in DRAM, that's not a good idea. Can anyone guess why? So basically, you're copying one array to another array, and you do it completely within DRAM. Yes? Yes, exactly. You may need that data that you're copying, right? You may need that destination page. So you need to be intelligent about this. If you actually need that destination page, you may want to bring some of the data back into the caches. You could do it that way, or you could say, in some cases, I don't want to do this in DRAM. Right? So it's a trade-off. And there are mechanisms in the paper that discuss how you actually achieve that trade-off. But you can actually get significant overall application performance benefits, at least for these applications, with the row clone. And with multi-core, benefits improve. Why do they improve? Because if one application is doing a page copy and the other application is actually accessing the memory system, now we're getting rid of that bandwidth contention this application that's doing the page copy is causing to the other application. So with multi-core, doing operations in DRAM becomes much more interesting, assuming you can do that low cost. Okay, any other questions? Okay, I encourage you to think about doing similar operations in DRAM, bulk operations in DRAM. But the key, again, needs to be low cost. You don't want to add a huge processor within DRAM. That just doesn't work. And I don't think that's going to work for a while. Okay, so I don't think I'll cover the ongoing research significantly, but I'll point you to some papers. So one thing we talked about is the retention time. If you're interested in that, I'd point you to this paper. I already talked about more computation in memory and memory controllers. It's a very important research area going forward, I think. And getting rid of the refresh overhead going forward is an important research area. So let me summarize this DRAM scaling part, which is the end of topic 1, and then we'll jump to topic 2. So in the last 2.5 lectures, we've covered major problems in DRAM scaling and design. And we've focused on especially 4 things: high refresh rate, high latency, low parallelism, and bulk data movement. And I've discussed 4 new DRAM designs after discussing the basics. This is just a sampling of what you can do in this area. Raider, reduce the refresh impact. Tiered latency DRAM, reduce DRAM latency at low cost. Today we've discussed subarray level parallelism, which reduced the bank conflict impact by improving DRAM parallelism. And we've also discussed row clone, which reduces the energy and performance impact, bulk data copy, and initialization. So all 4 designs have some things in common. They improve both performance and energy consumption. It's not a trade-off, actually, in many cases. They're low cost, and I believe changing DRAM requires this characteristic to be there. They enable new degrees of freedom to the software and controllers. So they actually break this interface that exists between the rigid interface that we have to memory today. And what are the degrees of freedom? Subarrays, for example. The ability to move bulk data within DRAM. Or a portion of DRAM that's really fast. These are new degrees of freedom that can be taken advantage of at the higher levels of the system. And this is why I called it the system DRAM co-design, because if you not take advantage of this freedom, I don't think you'll be taking advantage of the overall, of these mechanisms to optimize the overall system. So I think going forward, rethinking this DRAM interface and design itself is essential for scaling DRAM itself. And we'd probably like to co-design the DRAM with the rest of the system by exposing it more, but in an intelligent way. So these are a couple of other papers you may want to look at. Characterization of commodity DRAM chips, is what I talked about. And actually, One other area in DRAM is power management, and this is an area that has not been focused on a whole lot except for 3D stacked DRAM. But you would like to do aggressive power management in DRAM, like voltage and frequency scaling. There are interesting circuit level issues there. If you're interested in that, I'd be happy to talk about that too. But that's the end of topic 1. Now I'm going to switch to do a mini context switch to topic 2. But if you have questions, you can shoot now. Okay. Any questions? Yes, Arvind. That's a great question. So we've actually been working with some DRAM manufacturers, getting a lot of feedback in developing these techniques. It's very hard to tell which techniques are most likely to be used. I think they've expressed interest in all of these techniques. And subarray level parallelism, for example, is something that could be used in the future. Its overhead is low. And it for example, in GPU-like applications, it enables so much bandwidth that the benefit that you get is very high. Radar has issues in the sense that you need to figure out the retention time profile of the cells. If you have a very good retention time profile, the overhead of radar is very low. So that could be used pending you get good retention time profiling mechanisms. Tiered latency DRAM also, there's good feedback on that. So I believe all of these techniques have the potential. Maybe and row clone actually is probably the easiest one to be implemented because it really requires almost no change within the subarray. I believe these techniques are easier to use if you do not have to break the interface and if the companies do not need to agree on that interface. So the main limiter to use would be JEDEC rather than the technical aspects of the ideas, of these ideas at least, except for the radar idea. So now that said, if you have 3D stacked DRAM where you're not bound by this interface, or if you're manufacturing DRAM that's embedded DRAM where you're not bound by this interface, you could apply these techniques right away. And I do not know if people will tell us if they use these techniques in that case. But even changing the interface such that you can do an activate and after another activate, that will probably take years in JEDEC. Yes. That's right. But I think going forward, that's changing because the cost of scaling at the circuit and device level it's increasing exponentially. So they'll have to bite the bullet and say, okay, we're going to do some architectural changes that will increase our cost, but that'll increase our cost much less than what we would have paid by investing in circuits and devices and trying to do this in a much more difficult way.